So, in this class, we will discuss the fundamental terminologies and fundamental concepts regarding the alternating voltage or alternating voltage and alternating current. So, in your plus two classes, you might have studied the alternating current waveforms, alternating current and alternating voltage waveforms, how practically it is being generated, like that, right? So for the time being, I'm not discussing that into detail. What we will do is we will have the discussion, that is actually we will have an introduction. Today, nowadays, the vast majority of electrical power is generated, distributed and consumed in the form of AC power. That means in your house, in your houses, then commercial applications, then industrial applications, and all other applications that the voltage, sorry, the power is in AC form, alternating form. That means the generation by in Kerala, it is KCB. Actually, KCB is generating a few megawatts. That's all. In India, there are many, like your NPCL, then yes, the NPTC, like that. Okay, and the generation, then the distribution, and also consumption is in AC. AC form. AC means alternating current. AC form. That is alternating current. Such a current reverses its direction periodically. And alternating voltage also, its direction will be periodically alternated between positive and negative polarities. That means, let me take the example of alternating current. That is nothing but it looks like this. I'm drawing the y-axis and here the x-axis, like this. Okay, x-axis, y-axis. We have the AC current. Even though this AC is already, we have alternating current, its expansion, but we will the terminology is AC current, AC voltage, like that. Okay, it is actually alternating voltage and alternating current, but our terminology is AC current, AC voltage, like that. Okay, so don't you need not to have that doubt. It's a simple doubt. Okay, that means you ignore it. Okay, I will be saying AC current, AC voltage, like that. Okay, and we have the sinusoidal waveform like this. Just like this. Pure sinusoidal, actually. Okay, and this is, I am notating it as small letter I, that is instantaneous value of current, and on my y-axis this I is I'm taking, and on x-axis I'm taking theta, that's equal to omega t. Okay, so this is 0, and we have peak value of this alternating current I at theta equal to pi by 2 and at theta equal to pi, this is pi and this is 3 pi by 2, 2 pi and so on. Okay, and we have so we learned that in our +2 classes this I is equal to Im sin omega t, where Im equal to maximum value of current. So in this waveform we have Im is equal to this red, this is Im plus Im and this is minus Im minus P, that means negative P minus Im. Okay, and yes, and we will discuss the the terminologies related to this AC waveform. Terminology. So first terminology is cycle. What do you mean by a cycle? Cycle is nothing but the values of sine wave repeat after every 2 pi radians, that you know mathematically. One complete set of positive and negative values of the function which goes on repeating is called a cycle. Okay, so in this case we have 0 to 2 pi. After 2 pi all the values are repeating for this waveform. So after 2 pi the waveform is repeating. So the section the time period or the time period in terms of angle after which the waveform is repeating is known as a cycle. Okay, and in one cycle the value of current I increases from 0 to a maximum value and decreases through 0 to a negative maximum value, that is minus Im, and then again increases towards 0. Okay, and then so this is our one cycle. This is one cycle, and the time duration corresponding to one cycle is known as time period. Time period, capital T. T equal to time period. And here capital T is equal to 2 pi radians. Actually this is actually omega t, that is angle in terms of angle actually, but in seconds it will be theta is omega t, and this omega t will be equal to 2 pi radians and t will be equal to 2 pi by omega second, that's equal to capital T, time period. Okay, that is defined as the time period. That is one cycle that expressed in second. Okay, time that expressed in time is known as the time period. Then the next terminology is our maximum or peak value. Maximum or peak value. Maximum or peak value is the maximum value denoted as IM, I maximum, IM notation. Positive, maximum value positive or negative of the quantity. Okay, and it is also sometimes known as the amplitude of the sinusoid. Amplitude. That means this plus Im or minus I. That is known as the peak value or maximum value of the waveform. Okay, and it occurs in this case it occurs at theta equal to pi by 2 and theta equal to 3 pi by 2. Now instantaneous value. Instantaneous value. Instantaneous value is nothing but we have denoted, or our notation is small letter I here. So in electrical engineering these notations are very important. Okay, this is how I in my subject I will teach the AC fundamentals, and also in the next module also I will simply write this IM, I, small letter I, small letter V, capital VM, like that. So on saying that notation, you should recall that that is nothing but our maximum value. Okay, that you should remember it. That you should be able to recall it. Okay. Now, yes, instantaneous value means it is the value of the quantity at any instant of time. Okay, at any instant of time. And the fourth one is time period. Yeah, time period that we have already defined. Time period or periodic time, you will say periodic time. It is the duration of time required for the quantity to complete one cycle, and it is denoted as capital T. Notation, again notations are very important. Now frequency is nothing but F is equal to 1 by T, reciprocal of time period, that is the number of cycles per second. Okay, number of cycles per second. It is the number of cycles that occur in 1 second. It is denoted as F, small letter F, or nu. Nu also, and another notation. The unit of frequency is hertz. And the frequency of supply in India is 50 hertz. 50 hertz. That means yes, you look at your watch, and when you see 1 second, okay, on completion of seeing 1 second, your electrical supply waveform, okay, which is present in the form of current, okay, current in your house will complete 50 number of cycles, okay, and that means the time period T will be equal to 1 by 50, that's equal to 20 millisecond. That means when you close your eye and open your eyes, within that duration of time, 50 number of cycles are completed for your electric voltage, your supply voltage. Okay, that is the meaning. And in other words, that one cycle is equal to 20 millisecond. Okay. Yes. Then we have the another term we have angular frequency. Angular frequency. Angular frequency omega. The values of a sine function repeat after every 2 pi radian, right? The angular frequency denoted as omega is equal to the number of radians covered in 1 second. 1 second. That its unit is radians per second. Okay, radians per second. And since one cycle covers 2 pi radians, that means one cycle equal to 2 pi radians. Okay, 2 pi radians. And there are f number of cycles in 1 second. F number of cycles in 1 second. So the angular frequency is given as omega equal to, you multiply 2 pi n to f. That much radian per second. Okay. Yes. And that's equal to 2 pi by t. Again, radian per second. Okay. And next terminology is alteration. Alteration. Alteration means this one half of the cycle. There are two halves for one cycle, positive half and negative half, and the one half of the cycle is known as alteration, when it includes either all positive or all negative values. Okay. Then yes, that's about your terminologies. Then we have yes, we have to solve one example problem. Yes, a sinusoidal voltage question is a sinusoidal voltage is given by V is equal to 20 sine omega t volt. Question A is, at what angle will the instantaneous value of voltage be 10 volt? At what angle, that means theta, at what value of theta will the instantaneous value of voltage be 10 volt, and B question is, what is the maximum value for the voltage and at what angles? What is the maximum value for the voltage waveform for the AC voltage and at what angle? Yes, so he has given yes, the given P is equal to 20 sine omega t. Yes, and also we have the standard form V is equal to M sine omega t. On comparison, we will get maximum value as 20. V max equal to 20. And that means, and the first question is the angle is at what angle will the instantaneous value of voltage be 10 volt? That is for our first question. So given that the instantaneous value of voltage is 10 volt, so small letter v is 10, and that's equal to 20 sine omega t. So sine omega t is equal to 10 by 20, that's equal to 1 by 2. That means omega t is equal to sine inverse 1 by 2, that's equal to 30 degree is the answer. Okay, now next, what is the maximum value for the voltage and at what angles? Maximum value of voltage is 20, and this can be plus 20 or minus 20. So for plus 20 we have plus 20 is equal to 20 Vm sine omega t. That means Vm is equal to 20 sine omega t only. So omega t is equal to sine inverse 1, that's equal to 90 degree, and minus 20 is equal to 20 sine omega t implies omega t equal to theta is equal to sine inverse 1, that minus 1, that is equal to 3 pi by 2. Right, yes. So we have solved the two questions. Right, now we are moving on to the next topic, that is nothing but your average value and RMS value or effective value. Okay, that means average value and effective or RMS value, effective or RMS value of any waveform. So for any waveform, whether it is sinusoidal, triangular, square, or any waveform, average value and RMS value, both these values are defined. Okay, and this average value is like your average value is equivalent to the what okay, RMS value and average value, these are two definitions. Okay, and we will learn actually these two values got a meaning in electrical engineering, but that is not required for you, I think. And we will define what do you mean by average value and what is RMS value. So that is enough for you. Okay, for electrical engineers, the meaning of that it is required. Okay, for you it is not required. So I will just yes give you the formula. That is, I'm defining the average value of voltage waveform, or average value of current waveform. Similarly, you can define. First of all, I am defining the average value of voltage. Okay, and it is the algebraic sum of all the values. Okay, it is the algebraic sum of all the values divided by the total number of values. That means, and this is exactly what you do while finding the average marks for a class of students. That means you have in your class, suppose your total strength is 69. There are 69 students, right? And 69 students, we have got 69 marks. So average of that marks of students in your class will be some first person mark, that is x1, that will be x1, x2, x3 we will say, and etc. up to x69 marks we will add, and we will divide that by the total number of students, that is 69, right? And the same way we are finding here the average value. That means, yes, it is the sum of all the values. Okay, all the values divided by the total number of values. That means I'm going back to my waveform here. So here I'm taking so many instantaneous values. Okay, instantaneous values. Let it be this at this theta, that is theta 1, we have I1, we have I2, I3, I4, I5, etc. IN we have. Okay, and similarly for theta 1, theta 2, theta 3, etc. theta n. And similarly in this negative half cycle also we have IN plus 1, IN plus 2, IN plus 3, etc. Okay, I2n we have. And the average value means you take the algebraic sum of all these instantaneous values, that is I1 plus I2 plus I3 plus I4 plus etc. plus IN, that is positive half cycle completed, then minus IN plus 1 minus IN plus 2 plus minus IN plus 3, etc. minus I2n whole divided by 2n number of values. So this is what I mean by average. So for every I1 in this positive half cycle, we have a negative value in the negative half cycle. So what happens is I1 and minus of I1 will be get cancelled. So what we will get is 0 value. So average value of an AC waveform, whether it is current or voltage, the average value is 0. Okay, in this case, suppose we have a waveform like this. We have a waveform like this. Okay, we have a waveform like this. So in this case, and in the previous example, we have considered the points up to 2 pi, right? So why? Because after 2 pi it is repeating. The same values are repeating. So it is enough to compute or carry out the averaging, averaging or the operation up to values for 2 pi. After it is whatever the waveform is, if you apply, the same result will be there. So in all the cases, we will have a general formula. We will have a general formula for average value, and it is given by average value is given by V average, VAVG, that is average value of voltage, is equal to area under full cycle divided by length of one cycle. Length of one cycle. Okay, this is the definition. That means for the previous example, if you consider the area, okay, area that is positive area, we got positive area for the entire full cycle, that is for one cycle we have positive area here and we have a negative area here. So if you algebraically sum these two areas over one full cycle, then positive area plus minus negative area divided by the cycle length. Cycle length is nothing but 2 pi. So this will be your average value. So again you will get 0. Okay. And if you consider another waveform like this, whether this is voltage waveform V and maximum value of that waveform is capital Vm. This is omega t on x-axis. This is 0. This is pi by 2, and this is pi. Okay. So in this case, and this is 3 pi by 2, and this is 2 pi. And in this case, the waveform is repeating after pi. That means 0 to pi we have one wave, one cycle, and in the another cycle that which is repeating after pi, then pi to 2 pi, the waveform, the same values are repeating. So the time period t here will be equal to pi. That means the cycle length is equal to cycle length here is equal to pi. So I am going to find the average value for this voltage waveform, that is VAVG is equal to, by definition it is area under full full cycle divided by total length of cycle. Okay, now then what you will get is we have this waveform formula. We have V is equal to Vm. We are going to define this waveform, that is V equal to Vm sin omega t for omega t greater than 0, less than pi. Okay, greater than 0 and less than pi. So this is our waveform. V is equal to Vm sin omega t. Now we have area, means we are going to apply the integration, that is area is I'm considering a small differential length, that is d theta. I am considering d theta or d omega t, both are equal, and this is infinitesimally, and this d theta tending to 0, or d omega t is tending to 0. That means the width of this rectangle is reducing and it is tending to 0. That means it becomes a vertical line. So, and this I am considering this length height as v, because this at this point when d theta or d omega t tends to 0, this point and this point will coincide, so it will become a point, a single point, and that is nothing but v, that is equal to Vm sin omega t. So the area, the shaded area, is given by the equation height into width, rectangular area, that means v into d theta or v into d omega t. So that means Vm sin omega t d omega t is the small area here. So if you want to get the entire area, this entire area over one cycle, then what you have to do is you have to integrate this between the limits 0 to pi. So integral Vm sin omega t d omega t integral 0 to pi, and that is what you mean by area. Okay, and then the base, that is length of one cycle, is equal to length of one cycle is equal to pi. So average value of the waveform, that is V average, is equal to integral 0 to pi Vm sin omega t d omega t divided by pi. That is equal to Vm integral Sin omega t d omega t 0 to pi by pi, that's equal to Vm by pi sin minus cos omega t 0 to pi, that's equal to Vm by pi cos 0 minus cos pi, that's equal to Vm by pi. Cos 0 is 1, cos pi is minus 1, so plus 1, that's equal to 2 Vm by pi. So this much volt. So this is our average value of the waveform. And similarly, we can prove the average value of alternating waveform is 0. Like and then at that time, what happens is I average will be equal to base value will be, that is length of one cycle will be 2 pi, and the area will be integral 0 to 2 pi Im sin omega t d omega t. Yes, the concept is same. So what you will get is Im by 2 pi you will get, and integral 0 to 2 pi sin omega t d omega t. So integral 0 to 2 pi sin omega t d omega t is nothing but 0. So I average will be equal to 0. Yes. So that you can prove it. Now we are going to discuss the next value, that is RMS or effective value. Effective value or RMS value. RMS value means root mean square value. Okay, that means you have to read it in the reverse manner. That is, you have to square your waveform first of all. Okay, square. Then you have to find out the mean value, and then you apply the root. That is what I mean by root mean square value or effective value, otherwise known as effective value. So the effective value of an AC current waveform, actually for AC current waveform average value is 0 for one cycle, but the average value is 0 means it doesn't mean that its RMS value is 0. It has got RMS value, average value is 0, but it has got RMS value. Why? Because we are squaring the yes, we have the waveform like this, right? Yes, waveform like this. So we have the positive values and negative values. So what we will do is we will square this waveform. Then what happens is this positive value when squared will become positive value, and the negative value when squared again becomes positive value. Okay, so we will get a waveform like this. Okay, like this, and we are taking the mean of this waveform, and we are applying the square root to that. That means if you are taking the mean value to this, then we got only the positive areas only. So there will be some value and we are taking the square root of that definite value. Then you will get, finally you will get the definite value. Okay, so you cannot say that the root mean square value of a alternating current waveform is 0, even though its average value is 0. Okay, so just let me consider again the same figure, same waveform. Then yes, we are squaring it, means all the values are get squared. So you will get, that means I1 is squared, I1 square you will get, then I2 squared, then I3 is squared, like that. So what happens is I1 squared plus I2, then you are taking the mean of it and also applying the square root of that. So that means I1 square plus I2 square plus I3 square plus etc. plus I2n square whole divided by, sorry, whole divided by the number of again the number of values. So there are 2n number of values, so 2n, and then we are applying square root to this, like this. So this is what I mean by RMS value, that is root mean square value. So but in practically, for computing the RMS value, we have the formula like this, that is RMS value of voltage, that is V RMS will be is equal to integral V square d omega t, okay, divided by the length of one cycle, that is capital T, and square root of the entire. Yeah, this is our formula. So what happens is, for our alternating waveform, we have this as, yes, so yes, we are going to find out the RMS value of this alternating current waveform. So if you square this whole waveform, then positive will become positive and the negative values also becomes positive. So the waveform looks like the red colored waveform. Now you are finding the mean of this, and finally you are applying the square root. then that means this red colored waveform is nothing but your waveform I square. So again, in order to find out the area of this waveform for one cycle. So here the one cycle is reduced from 0 to pi, and after pi this waveform all these values are repeating. Okay, so 0 to pi. So the length of one cycle will be pi. Pi in this case actually but our initially the base value length of one cycle in this case, in order to find out the RMS value, it is not pi. Actually it is not pi, it is 2 pi. Okay, that means length of one cycle of which waveform is considering is important. We are finding the RMS value of this alternating current waveform. So one cycle is nothing but the one cycle of this alternating current waveform, not the squared waveform. Actually, the squared waveform cycle is pi only, but since we are finding the RMS value for this the entire alternating current waveform, the length of one cycle will be 2 pi. Okay, so this is I square, and in order to find out the area, I am again considering a strip like this. Okay, and we have the width of this strip as d omega t or d theta, and this height of this strip is nothing but I square. So the area will be equal to I square d omega t, and you have to integrate it from integral 0 to pi only. 0 to pi only. Why? Because we have the area here. Area is only extending from 0 to pi. So we have to find out this area. Okay, and the base is 2 pi. Right, so integral, we will get it as integral 0 to pi. Okay, actually it is integral 0 to 2 pi. Okay, right, integral 0 to 2 pi, because since we are finding out the effective or RMS value of the entire waveform, that is alternating current waveform, entire waveform. So we should have the entire area, right? So integral, we will get integral 0 to 2 pi I square d omega t. So this is the area, and then area divided by base, that is 1 by base value is, that is base means length of one cycle of alternating current waveform, that is 1 by 2 pi. Okay, and finally apply the square root like this. Okay, so that means we will get VRMS I'm squaring on both sides, LHS as well as RHS. So VRMS square will be equal to 1 by 2 pi integral 0 to 2 pi I square d omega t, and I am writing this I as Im sine omega t d omega t Im square sine square, that's equal to 1 by 2 pi Im square integral 0 to 2 pi sine square omega t d omega t. So that will be equal to Im square by 2 pi integral 0 to 2 pi sine square omega t is nothing but sine square omega t is 1 minus cos 2 omega t by 2. So integral 0 to 2 pi d omega t. So if you uh, solve this integration, then you will get, sorry, no, this is not VRMS, this is IRMS. This is nothing but your IRMS square. Okay, IRMS square. Sorry, this is IRMS, and previously also this is IRMS. Okay, IRMS. Now on solving this, we will get IRMS as IRMS is equal to Im divided by root 2 ampere. So this is our RMS value of the AC waveform. AC waveform. Okay, this AC waveform RMS value. So what will be the average value of this waveform? It will be 0, absolutely 0. Okay, so that is what our average value of a waveform and RMS value of a waveform. Yes, then we will we have to define another term known as form factor. Form factor or peak factor. Peak factor of a waveform, and it is defined as the ratio of the the ratio of the effective value or RMS value to the average value of a waveform. So in this case, we have the form factor or peak factor is equal to RMS value divided by average value of a sinusoidal or alternating current waveform. So the form factor of this alternating current waveform will be equal to F will be equal to RMS value of the alternating current that we got as Im by root 2, and the average value of the waveform is we got it as 0. So form factor for a pure sinusoidal pure alternating current waveform, it will be infinity. Okay, and for our supply voltage, that is 230 volt 50 hertz supply voltage, which is available in our house, actually its form factor is 1.11. But the interesting point here is uh, if our supply voltage, okay, if our supply voltage is pure sinusoidal alternating current waveform, it should be infinity, or it should be very high, greater than 1, very much greater than 1. But the form factor for our supply voltage waveform is 1.11 only. So that means your house, the supply voltage provided by the KSCB is not pure sinusoidal. That means it has got some average value also. Okay, some average value also. Okay, that's about our terminologies as well as some definitions like form factor or peak factor. Okay, so thank you.